So we are going to record the session, and I hope by early next week we will have the recording available as well as the slides for everybody's future reference. And we will wait maybe 2 more minutes before we start. Hey, welcome, folks. It's 1 o'clock now, so I think we'll give it maybe 2 more minutes and then we'll start, and folks who join us later will catch up. This session is being recorded because we will make the recording available, hopefully by early next week. All right, folks, let's get started in the interest of time. Very suitable in light of the topic of today's webinar. So welcome to the Bridges-2 webinar to be presented by Professor Dubrawski and Dr. Goswami of the Artur Lab at CMU. So in particular, I mean, this is under the auspices of the Pittsburgh Supercomputing Center, which is a joint project of CMU and the University of Pittsburgh since 1986, and going strong. And in particular, welcome to the Bridges-2 project, which probably many of you are familiar with because I think many of you are users of the Bridges-2 system. So it is under the auspices of the Bridges-2 project that we organize this webinar series. I'm Sergio Sanjelevic. I'm the PI of the Bridges-2 project, and it is my pleasure to honor you, to welcome you on behalf of our leadership team. This is our leadership team. And so we organize these webinars as a forum for the Bridges-2 community to learn and share ideas and achievements. And we're looking for topics and speakers of interest to work that is being done by folks on Bridges-2, or not just on Bridges-2, and also plans for the future, emerging projects. So if you have any ideas about future speakers, and including yourselves or your own group or topics, just please let me know at this email address. So today we are honored to have two speakers from the Artur Lab at CMU. Professor Dubrawski, Chair of Computer Science at Carnegie Mellon, where he directs the Artur Lab, one of the largest applied machine learning and AI teams in academia. Artur has worked for more than 3 decades on the forefront of development of AI, serving in technical leadership roles in industry and leading multiple research endeavors in academia. And Mononito Goswami is recently graduated with a PhD in robotics from CMU. He's interested in developing foundational machine learning models for real-world applications. His research tackles the limitations of traditional machine learning approaches, focusing on scenarios with inaccurate, decentralized, and insufficient data in an effort to democratize machine learning. He led the development of one of the first open source foundation models for time series data, and I think this is the subject of today's talk. Finally, a couple of notes on the logistics. So we do follow the code of conduct by access, because most of Bridges-2 is part of access, so we do that. All of us except the speakers will be muted during the presentation, which is going to be roughly 50 minutes. While during the presentation, please type your questions into the Zoom chat, and then we will have 10 minutes at the end to answer questions live. As I said before, the video recording and the slides of the webinar will be made available specifically from this link next week. With that, are there any questions for me to begin with? If not, then let me stop sharing and invite our speakers to share their screen, and please begin their presentation.
Thank you very much for inviting us here. It's a great pleasure to talk about our recent work in time series foundation models, and perhaps also add some remarks on the state of the AI and how it should or could impact our society through large-scale computing. Today I'm joined by Mononito Goswami, who was my PhD student, but now is my PhD colleague. He defended his thesis, very much aligned with the topic of today's presentation last month, and he's ready to take over the large industry in this country with his ideas and his productivity. Next slide, please. So we come from the Artur Lab, which indeed is one of the largest research teams in academia, focusing on applied AI for more than 30 years now. We are unusual for academic standards in some ways, including our fixation on making impact in the real world. So really enjoy pushing our tools to practice and to the hands of end users of our technology, which in turn gives us an opportunity to learn about the limitations of the current AI technology and fill the gaps that we discover with our fundamental research. Next slide. AI is not new. It has been around for a few decades already, but it was mostly, present in the academic environments, in research venues. Only recently, we observed this massive expansion of the exposure of this technology to even general public. And I keep joking that if you go to the street of any large city in developed country and you ask a randomly selected person from the crowd walking around, if they may be an AI expert, I guess 50% of them would say yes, which is great, but also carries certain kind of risks that we want to systematically address. Even though the domain itself is not new, we do not really have a formal way of systematically building useful solutions using AI. Here at CMU, we are making some attempts to structure our approaches. So one component of this initiative is the diagram that you see to the right of the slide. We call it AI stack or AI capability stack. And it basically is nothing really new. It just shows a layered structure of different capabilities and competencies that need to be considered if someone wants to make AI tool a successful tool that makes difference in practice. it's very hard in my professional experience to really deliver solutions to the endpoint unless you at least consider every layer of this, every slice of the stack. Next slide, please. I would like to also complement this diagram with another axis that represents what I call artificial intelligence project cycle. If you look at the subsequent steps of this cycle, they are not really unique for artificial intelligence that much. Any IT project may be structured this way. So again, in order to be successful, we need to consider all those steps, from data capture to how we assemble the data and curate it, how we make data ready for AI, perhaps by labeling it for training models. Only then we can have fun with what most of the researchers here at CMU want to do, which is build new models and demonstrate their capabilities. And then, in industry, we also want to deploy those models in practice and integrate them with broaderly scoped systems. Next slide. There's two dimensions. I think we skipped one. Yes, there's two dimensions form what I call capability grid of AI. So this intersection actually creates those number of cells. And if we go to the next slide, you will see that I populated them a couple of years ago with some of my particular choices of what at that point I thought was missing. Many of those items are still missing in our portfolio of capabilities that are required for AI to truly make systematic difference in the world. So if you're an AI researcher, you are not done. We are not done. We have plenty of things to work on. Next slide. What's unfortunate is that in academic environment, we sometimes, quite often actually, self-limit ourselves to only worrying about the small subset of the range of the project cycle presented below, which actually diminishes our ability as a community to deliver societally impactful progress as a result of our work. But this is my personal pet peeve. I want to make sure that if we have academic community members in the audience, that they would try to agree with me and maybe help us change this particular situation. Next slide, please. And then when you look at, what are the limitations, what are the sources of limitations that prevent AI to make really impactful difference in the world, you can source them back to either data issues with the models we are building on the data that we have. And of course, humans also can play a role here. And today we'll be mostly focusing on the issues of data-driven limitations. Perhaps the most common limitation involving data is the lack of it, right? So usually we in practice, when we have a problem we want to solve, we may not have data to build to train a model, or maybe we don't have enough of this data, or maybe its quality is limited. Especially even if we sit on a large pile of data, it may not be annotated for training predictive models. So today's topic is a one big push to address these issues by building pre-trained large models that we expect to know everything about everything. We call them foundation models. And today we'll focus on a particular subset of those models called time series foundation models. Next slide. And here, by cosmic coincidence, our team, without knowing, ended up in the forefront of the development of time series foundation models. I assume that everyone in this call must be familiar with large language models, which are foundation models for text, perhaps also with large vision models for visual data, images, and videos. These two data modalities, text and visual data, have been very well addressed by industrial endeavors into foundation models development and application. And so we in academia, we cannot really compete head-to-head with industry, which from our point of view have unlimited access to expensive GPUs and CPUs. So we instead focus on the niches that industry leaves behind. One of these niches is time series data, very prevalent in healthcare, in finance, and hundreds of others areas of human interest, as well as tabular data. Today, we'll focus on time series, and in particular on Moment, which is the first open source multitask model that has become immensely popular across community of both researchers and practitioners of time series analytics. And Moment has been developed by our very own Mononito Goswami, whom I'm going to hand over this presentation to right now. And you're muted, Mono.
Thank you so much, Professor. I hope everyone can hear me now. Okay, let's get started on imagine that you are a neurologist and you want to detect seizures using brain EEG data. Now, you'll have to sieve through hours of this data, sampled at 240 hertz from not one, but 21 different leads. And basically, you have to look at a very long multivariate brain EEG time series to detect seizures. But that's not all. To make an informed decision, you must also review complementary information, such as biological covariates in the form of text data or the blood report in the form of tables. You'll have to review highly multimodal information. And to do that, that is our doctor, has to spend over 15 years studying and countless hours away from direct patient care. Which brings me to my first challenge. Domain experts must review complementary, complex multimodal information to make decisions. Or instead, they can try to automate this process by building a machine learning model. Say you want to build a classification model to detect whether a time series shows a seizure or whether it is normal. To build a model, you'll first have to prepare data, pre-process it and label it. Next, you build a model, you'll train it and tune it. And finally, you'll evaluate it. And at this point, you'll probably have to go back, rinse, and repeat. Now, machine learning models once built can save time and lives. But building these models for a specific problem is tedious and repetitive. But this repetition and regularity is also where the opportunity lies. And I will frequently leverage this in a lot of what I have done and what we do in this lab. Now, our friendly doctor has spent a lot of time, resources, and effort in building a machine learning model. But in the real world, data is seldom ready for machine learning. Now, you have to accurately label your data. But if the nature of the problem changes even slightly, you'll have to start from scratch. And all of that is assuming that your data is located at a central location. But you might want to learn a collaborative model from, say, siloed data. And this brings me to my third and final challenge. Preparing data for machine learning is a slow, cumbersome, and error-prone process. Alas, you have to repeat this effort for every new data set and every new task. So this specific example highlights three key challenges which limit the widespread adoption of time series machine learning. Building ML models is tedious and repetitive. To accurately model real-world data, just as domain experts do, ML models must be able to review large volumes of highly multimodal information to make decisions. And finally, building ML models is bottlenecked by the time-consuming, cumbersome, and error-prone process of preparing data. And in our work, our goal is to develop tools to address each of these challenges. In this talk, we will focus on the first two challenges, but we'll be happy to chat about preparing data for ML offline. Now, building ML models is hard. It also requires experience. But what if we could build good time series ML models faster? What if we had time series foundation models, which given time series from different domains, could solve multiple tasks such as forecasting, classification, and more without much training or effort? In the first part of the talk, we'll present our work on Moment, a widely used family of open source time series foundation models, and convince you that it can and already has accelerated the time series ML development process. Next, we will imbue our time series foundation models with the ability to model long and multivariate and multimodal time series. Domain experts review complex multimodal information to make decisions, and so should our models. After Moment, we will present our initial work on InfiniMoment, a long context time series foundation model, and Jolt, our time series and text model. And until now, we've only focused on building capable ML models quickly. We've not addressed data challenges yet. For our models to be able to handle the challenges posed by real-world data, it is important for us to develop methods to encode expert knowledge, for example, to label data or for evaluation. And this is what a lot of our work focuses on, but we will not touch on this today. But we're very happy to answer questions if you have any or chat offline about this. The overarching goal of our work is to empower domain experts with powerful, capable time series models to rapidly build machine learning solutions with all the complexity of real-world data. Now, and to do that, to advance time series intelligence, our hypothesis, we believe that it is important for us to build capable foundation models dedicated to time series data. It is important for us to improve our understanding of these foundation models and also to address practical challenges that arise when common assumptions are violated. In the first part of this talk, we will demonstrate how specialized foundation models for time series data can accelerate time series machine learning. I'll discuss our work on Moment, the first family of open time series foundation models, and then we'll expand Moment's utility by building its long context and multimodal extensions. Now, advances in time series foundation modeling are very recent, and as such, little is known about what these models are learning. The next part of the talk will briefly focus on understanding these models to gain actionable insights with two goals: to improve our understanding of these models and their capabilities, and to improve their performance. Now, I'm sure you all know time series, but I'd still like to build common ground before we dig deeper into our work. When I say time series, I mean a sequence of numerical observations of a set of features obtained sequentially in time. Now, a typical time series is characterized by temporal relationships such as slow increases or decreases called trend, or periodic changes called seasonality. Different features in time series can often be related. And time series data is ubiquitous. It is found in many different domains, for example, weather, robotics, economics, and healthcare. And effectively modeling time series data can have profound impact. Now let's get started with the first part of the talk, where we'll discuss Moment. Now, I've been using the word foundation models a lot. What should foundation models for time series data look like? I believe they should have the same capabilities as what large language models have for text data. For example, ChatGPT can solve multiple tasks with fewer labels, it is multimodal, and cost-efficient once built. Therefore, I believe a time series foundation model should have three key properties. They should be building blocks for multiple time series analysis tasks. In our work, we show that time series foundation models can be used for classification, forecasting, anomaly detection, imputation, question answering, etc. They should be effective in settings with limited data, labels, and compute. And finally, we should be able to tune these models with in-distribution and task-specific data to improve their performance. Now, there are three major ingredients to develop any foundation model: data for pre-training, the model architecture, and training objective, and a benchmark to evaluate the trained model. For a large language model, examples of these would be the pile, decoder-only transformer with next token prediction, and the MMLU benchmark. However, for time series foundation models, all of these ingredients were missing as of February 2024 when we were building Moment, and I would argue some of these ingredients are still missing. there was no large cohesive public data set with time series for different data sets and domains, which we could use to pre-train a model. So we introduced the time series pile, a large and cohesive collection of over 13 million unique time series from 13 different domains, such as healthcare, economics, and weather. Time series has many unique characteristics, which makes large-scale pre-training tricky. So we found systematic solutions to reconcile these unique properties to unlock large-scale pre-training, which culminated into Moment. And finally, there were no benchmarks to evaluate foundation models for time series data. Existing benchmarks were small, task-specific, and did not evaluate the unique properties of foundation models, such as their zero-shot performance or scaling laws. So we built a benchmark to evaluate foundation models on 5 different tasks and also evaluated special properties such as scaling. In this talk, we'd like to go deeper into the design choice for time series foundation models. And the design space for any foundation model is huge. We'd like to specifically highlight 3 important questions. First, how should we feed time series to the model? Second, what architecture should we use? Should we use a transformer or stacked MLPs, which are popular in time series? And third, what should the model predict? First, let's talk about the architecture. We use an encoder-only transformer model. Now, transformers are very common in foundation modeling in other fields, but they've also shown promise in time series forecasting. Using a transformer also allowed us to leverage advances in transformer architectures for language modeling, as well as their efficient implementations. Finally, a transformer encoder has bidirectional attention, which is important for imputation where context can be on both left and the right-hand side. To feed time series data into the transformer, we divide it into disjoint time series subsequences of equal length called patches. Each patch is one token for the transformer model. Now, patches are great for 2 reasons. First, attending on patches instead of individual time series reduces the complexity of attention. And secondly, thinking about the pre-training task, masking patches instead of individual time steps is a much harder problem and forces the model to learn meaningful representations. And finally, we used mass time series reconstruction as the objective because we realized that all the tasks that we are dealing with, forecasting, imputation, etc., are instances of the mass time series reconstruction problem. For example, if the mass patches happen to be in the middle of the time series, the model is imputing. If they are in the end, the model is forecasting. In the literature, anomaly detection is typically solved using reconstruction or forecasting. And finally, to reconstruct time series, the model has to learn useful representations, which can then be used as features for classification. Now, we evaluated moment on 5 different tasks, namely short and long horizon forecasting, classification, anomaly detection, and imputation on multiple datasets from different domains, and compare it to state-of-the-art statistical and deep learning baselines. Now, I won't go over the results in depth, but we found that even with minimal hyperparameter tuning, it does really well. With all the parameters frozen, Moment performed on par with statistical baselines, for example, a REMA for forecasting. And by just fine-tuning 1% of the parameters via linear probing, it was competitive with state-of-the-art deep learning models such as Patch-DST for forecasting. So the key takeaway is that unlocking this performance requires large-scale multi-dataset pre-training. Once pre-trained, foundation models like Moment can accelerate the development of good time series ML models on multiple tasks and different datasets from different domains. Moment has been widely used in practice, and we will talk about it towards the end of the talk. But Moment, like most other state-of-the-art time series foundation models, can only model short and univariate time series. Next, we'll briefly talk about how we can change that and build long context time series foundation models. We believe that long context time series foundation models should be able to model both long and multivariate time series. In this talk, we'll only focus on multivariate extensions. The key assumption here is that we can, with relative ease, extend multivariate time series models so that they can model long time series. Now, in the ideal case, we would like to model multivariate time series with minimal changes to moment's architecture and training procedure. But this is tricky because moment is a transformer, and standard transformers were designed to model text, which is a univariate sequence of tokens of fixed length. Now, a knife solution is to take all the channels of the time series, concatenate them to form a 1D array, and simply pre-train moment with a larger context length. Now, this approach has many problems, but the biggest one is that it does not scale. Remember that the standard transformer has quadratic complexity of attention. Now, the key idea is to introduce memory in transformers. On the one hand, RNNs process a single token and can compute representations for arbitrarily long sequences, but they're slow and optimizing them is hard, but they can model long sequences as we desire. On the other hand, transformers take a sequence of tokens as input in parallel, which makes them really fast. And this sequence is called the context, but they do not maintain state information and can only model sequences of a fixed length. Now, our idea was inspired from infinite attention, which marries the best of both of these worlds. The key idea is to introduce a recurrent attention layer with compressive memory. And this compressive memory can store information from multiple channels, and the attention layer can then attend to a sequence of tokens in context and in the memory. In standard attention, we only attend to tokens in context. How can we then leverage the global information in other channels efficiently? We can add a memory unit where we can store cross-channel information. This memory compresses information from multiple channels. Then infinite attention proceeds in 2 steps. In the first step, key and value products from multiple channels are aggregated into the compressive memory. Next, the query retrieves cross-channel information from the memory, just like it retrieves information from context in standard attention. And finally, the information from global multi-channel context is added to the local context using a learnable beta parameter. If you set beta to 0, then we approach standard local attention. Now, moment with infinite attention, or infinite moment, has some nice properties. First, we made minimal changes to the existing modeling and training paradigm. Secondly, with a knife solution, we scaled quadratically with the number of channels, but with infinite attention, we only scaled linearly. Also, global multi-channel attention is invariant to the order in which channels are presented. And finally, we only added one trainable parameter beta per attention layer. So even the memory footprint doesn't grow significantly. Now, we evaluated both moment and infinite moment on multiple multivariate datasets and tasks. Here we're showing multivariate forecasting results on 3 datasets evaluated using the mean squared error. We see that infinite moment consistently improves over moment. The 2 key takeaways from our experiments were that fine-tuning beta parameters substantially improve performance. Recall that the beta controls how much cross-channel information is fused into the local context. We also found that multivariate modeling does not always improve performance. It will be interesting to study in what conditions multivariate modeling is significantly better than treating channels independently. Now on to the final section where we'll briefly discuss about our work on Jolt, one of the first multimodal time series and text models. We're interested in building time series and text jointly, and this is a rich problem space. We can take time series and text as input and predict either time series or text as output. In this talk, we'll focus on the problem of generating text when a time series and some textual context is given as input. And generating text conditioned on time series is a useful task. Throughout the section, we'll consider the problem of interpreting ECG signals, which are used to detect heart health. Doctors spend a lot of time away from direct patient care to provide clinical interpretations of ECG data. And this process is time-consuming, cumbersome, and error-prone. Some machine learning solutions exist, but they're either based on hand-designed rules and are not expressive and do not generalize. Other approaches do not model time series data directly and convert it to either images or graph. The key question is how can we scalably generate expressive text by directly modeling time series? The key idea is to align pre-trained foundation models. We can use Moment to learn useful, meaningful representations of time series and soft prompt large language models to generate coherent text. Now, our method Jolt aligns the rich embeddings that Moment learns with soft prompts to an LLM using a querying transformer based on the instruct blip architecture. We chose this architecture because Q-formal has been used in the literature to align image and text modalities for image captioning and visual Q&A. It also has some nice properties. We love the idea of bootstrapping existing pre-trained models and moving the burden of alignment to another transformer, which can now align time series and text based on textual instructions. It is important to stress that we are in uncharted territory. At the time of building Jolt, there were no established datasets, tasks, or generic baselines. To evaluate Jolt, we use the PTB-XL ECG classification dataset, which has paired ECG and time series and textual interpretations, and we created two new tasks from this data: ECG clinical summarization, akin to image captioning, and ECG question answering, similar to visual Q&A. You'll notice one thing. These statements do not look like natural language. And yes, you are right, because they are not. These are brief ECG statements in German translated to English. And on this data set, we found that given an ECG, Joel generated better clinical interpretations than BLIP2, which is a large pre-trained vision language model which takes an image of ECG as input. The first key takeaway from our work on Jolt is that time series data should be modeled explicitly instead of treating it as an image or a graph. And most importantly, for multimodal time series foundation models, we are bottlenecked by the quantity of good quality paired time series and text data, and not the technology. With this, we come to the end of part one, where we built capable long context and multimodal time series foundation models. Due to the paucity of time, we'll very quickly go over some slides, but I'd like to summarize what we want to do in this part. We want to demonstrate that understanding foundation models can also help us improve their performance. In this part, we'll specifically answer 4 questions. What are these models learning? Can we manipulate their predictions without training them again? Can these models reason? And do these models understand basic time series concepts? We are very happy to answer questions about each of these parts, but I'll go directly to the punchline, so we have time for questions towards the end. Okay. A quick recap of this section would have been that we would have shown that foundation models learn redundant representations, which can be pruned to improve efficiency, much like large language and pre-trained language and vision models. Through our work, we also showed that these models learn human interpretable concepts such as trends and seasonality, which are encoded in specific locations within the model. We have also demonstrated that we can leverage this to steer model predictions to imbue domain knowledge that is missing in the model. Next, through our work, we've also shown that these foundation models show sparks of compositional reasoning, and it is input patching that unlocks this form of reasoning in time series foundation models. And finally, we've also shown that when LLMs are used to model time series data, instead of time series foundation models, targeted and scalable model interrogation can reveal capability gaps, which we can then fix with steering. Now, prior to our work, domain experts worked alongside machine learning specialists to develop separate models for individual tasks, a resource-intensive process requiring substantial data, compute, and machine learning expertise. Now, in our work, we introduce foundation models as versatile building blocks for multiple time series modeling tasks. And in the near future, we expect LLM agents to leverage these tools, fundamentally shifting domain experts from being developers to strategic overseers. And we expect this evolution to decisively reduce human effort and transform how humans collaborate with AI across time series applications. In this part of the talk, I'd like to briefly discuss our ongoing work on LLM agents for time series AI. Let's quickly revisit our goal. We want to empower domain experts with time series intelligence at their fingertips, and our work until now has certainly provided tools that domain experts can use for their ML problems. But our tools, like most machine learning algorithms, expect at least some familiarity with machine learning to be used effectively. However, domain experts seldom have the time to learn to use these tools. So we wanted to make it easier for them to use the tools presented in our work. And this is where we believe that large language model agents come in the picture. We want to build agents which can operate with real-world complexities of time series data and orchestrate the entire machine learning process using the tools presented in this presentation. And none of this is far-fetched. LLM agents have shown promise in coding tasks and simple ML problems. But these agents are built and evaluated on Kaggle competitions, which is just the tip of the iceberg. Kaggle challenges are great, but they have well-structured inputs and outputs, minimal ambiguity, and very few time series tasks. However, seasoned machine learning engineers have to deal with much more involved problems. And therefore, we believe that building useful time series machine learning agents will require us to go beyond Kaggle competitions. And this is where our work on time series GYM is situated. To conclude my part of the talk, I'd also like to highlight some of the impact that our work has had. The time series file that we use to pre-train Moment has been downloaded over 10,000 times on Hugging Face. Our large language model interrogation to interrogate models on their time series understanding has also been downloaded multiple times on Hugging Face. And in the 1 year that that Moment has been released, it has received over 1.8 million downloads, 500 stars on GitHub, and over $2 million in investments. Others have used Moment for a variety of tasks. They've used it for solar flare forecasting, diagnosing machine fault, human activity recognition, building predictive analytics, and they've found it to be broadly useful for anomaly detection and classification. In healthcare, Moment has been used to model brain EEG signals, photoplethysmography, and intracranial pressure in the brain. Even some of my excellent colleagues in the lab have used Moment to model EEG and ECG with some success. When I compared Moment with one of the recent foundation models, Papa-Gay, I found something interesting. We found that Moment performs well against this custom-built domain-specific model that was pre-trained on more than 57,000 hours of data without any fine-tuning. In contrast, Moment has barely seen any PPG data. This is not our own work, but we do expect some fine-tuning might improve the results even further. Now I'll hand it over to Professor Dubrawski.
Thank you, Mononito. This was very crisp and useful presentation. Even though today you only see myself and Mononito Goswami, this work would not have been possible without engagement and strong contributions from multiple members of our team, probably more than a dozen by now. Some of those people's faces are shown in this slide, but also our external collaborators. Next slide. And very prominently among the external collaborators, we are privileged to list Pittsburgh Supercomputing Center, who very recently have worked with us to deploy Moment in a software as a service modality. So with this, most of the US government-funded researchers will be able to access the goods and capabilities of Moment remotely without even having to install the open source code or pre-trained models on their local machines, to hopefully scale from our perspective, the impact of this popular model. It's already very popular, as you have seen from previous slides, probably slowly becoming a most common benchmark to compare alternative approaches against. But also, increase its potential impact and help us identify any remaining gaps in its capabilities that we should address with our future research. So I'm told that it's very easy to get your hands on it in this new form, and we are very grateful for our partners at PSC for this collaboration. We're excited to see how it works and whether it will actually attract attention. So thank you very much, dear friends at PSC. And the next slide is going to be our last slide. I want to thank everyone for their attention, and thank also Sergio and others at PSC for inviting us to give this presentation. And we moved fast enough to leave plenty of time for Q&A. Thank you very much.
Thank you very much, Artur. Thank you, Mononito. This is fantastic. If you have any questions, by the way, about using Moment on Bridges-2, I think the slide there had a QR code that you can scan. But any questions about it, please contact help@psc.edu, and we will be happy to get back to you to clarify any issues or talk about it, arrange with our team to talk about it further. But with this, we do have 40 minutes for Q&A. I think I see maybe 2 unresolved questions in the chat. The first one is from Thomas. Thomas, would you like to ask it in person?
Sure. Thank you for the presentation, doctors. So how has the length of context been used in this case as time series data? But as some of you may know, in the LM space, the length of the context has, dramatically changed the performance in the modeling space in the languages. So how does it impact the time series? Thank you.
Mononito, would you like to address this, since I addressed most of the questions offline while you were talking?
Sure, thank you so much. I saw the chats popping up, and thank you so much for doing that, Professor. Yeah, I'd be happy to answer that. So you're absolutely right, Thomas. The context length is something that's very important, and in scaling it is likely to bring a lot of valuable impact to the field of time series foundation models. Right now, most of the models or the first kind of models that were time series foundation models which were built took anywhere between 256 to 1024 time steps as input. This can be years of data if sampled yearly, or maybe even within 1 second if sampled at 512 hertz, for example. Moment specifically takes 512 time steps, a time series of length 512 as input. Longer time series can be subsampled, and shorter time series can always be padded. But we are also conducting some research right now on extending the context length of Moment using advances that folks in large language modeling have made. In fact, the work that we presented on Infini Moment is, we are actively doing research on it, and the whole goal is to increase the context length of time series foundation models, so that we are able to not only take time series in context, we can take maybe other time series examples in doing context learning. We can take language data for multimodal modeling or other covariates. So yeah, we are working on it actively. We have some nice results to show as well. And
If I may add here before you conclude the answer, Mono. So yes, context length, if we can make it very long, then of course we expect a great boost in performances, but it's quadratically related to computational cost. So that's a limiting factor in the current designs of transformers. That's why we reached beyond transformers to the ideas behind recursive neural networks, as you've seen in the previous slides, to see whether we can utilize that to reduce the limitations due to scalability issues of transformers and extend the effective context length that way. So this is what Mononito calls infinite moment. That's our attempt to solve this issue. But we are not the only one aware of this limitation. So a large portion of our research community is looking at these issues. And indeed, some foundation models in time series domain actually don't use transformers. There are a couple of examples of models that use stacked multi-layer perceptrons instead. I think jury is still out, whether this or that approach is better. Currently prevailing solutions rely on transformers. We'll see where it goes. And we are lucky because our former team members also developed stacked architectures using MLPs. So we are competent on that side of the story also, and we will be able to pivot as necessary if we see that there is some breakthrough there. There is also a question from using moment to apply to econometric data. My memory is not very good. I don't know if we actually applied moment except for some benchmarks ourselves to econometric data, but I know that Mononito is tracking literature published by others on moment, so maybe he will have some direct recollection of any specifically econometric application. I know that we played with finance data, but that's not exactly the same.
We definitely have some economic data from economics and finance and the benchmarks that we've evaluated on mostly forecasting. So the M3, M4 benchmarks, which Moment has also been evaluated on, or have those time series, but I do not recollect any dedicated study for the use of using Moment in econometrics. But we'll be very interested in kind of partnering and looking at the value that Moment can bring to economics and econometrics.
Especially now that you don't even need to download anything because you have all these goodies available through Bridges-2.
Right.
And there is also a question. Sorry, yeah, follow up.
May I just to speak on this just for a moment? That was my question that you were discussing there. I just wanted to say I'm a domain scientist in brain electrical recordings from the brain. And I did have a point which was, I think, discussed at some length already about multiple time scales within a single data set. And I think that comes up in a lot of data sets. It certainly comes up in brain recordings, but it comes up in multivariate recordings that you mentioned. The tabular data is actually a time series also, but it's sampled very slowly. The other thing that I wanted to point out about these multivariate time series is that it would be interesting to be able to handle thousands of variables rather than, 30 or 40, whatever you were sort of indicating. I asked the question about econometrics because I suspect that a great majority of the people who are interested in time series analysis want to make money, and they want to be able to forecast 5 minutes ahead. And I wonder. I think it's something worth at least thinking about, and I think it's something worth the Bridges people thinking about too, because there's no particular reason why I can't get an allocation to study the brain and then use a piece of it to be a day trader. And I think it's a real issue. I think a lot of the industry expenditure on machine learning is about predicting the future of econometric variables and making money.
This is a very interesting point, actually. Very interestingly, I think a part of the screen is kind of obfuscated by this thing, which I don't know how to remove. But in some of these kind of studies that I've summarized here, most of the work was actually not done in the finance field. We have seen a lot of work, in fact, on clinical waveforms, and we have partnerships with folks at UPMC as well who have evaluated moment for EEG data. So we are, as a lab, certainly interested in applications of healthcare, which furthers us as a society. And yeah, but I've also not seen a lot of research on these time series foundation models right now from the finance field. So that's an interesting point that I wanted to kind of highlight very
Just
quickly.
I
a
also
simple
wanted
point, a
to
simple
add a
point
word on.
about that
Yeah,
is
sorry.
that people who are doing that kind of work are not going to publish it.
Yeah, that's very likely as well.
And
You
about the
know,
multi-scale question, so if you have multiple processes represented in a convoluted time series, we actually have been thinking about it, and one of the utilities we expect to gain from the multivariate extension to moment is to be able to decompose our input time series into multiple timescale components and then feed them independently or in conjunction to the model to leverage this kind of structuring data. And that's easy to do, relatively easy to do if we have prior knowledge that such structure may exist in data. But even if we don't, I presume we can envision inferring the existence of such structure by optimization.
I think
So-
we can still maybe address Emily's question.
Oh yeah, that's right. Mononito, this is exactly in your court.
Yes,
I know
absolutely.
you like answering this kind of questions.
No, and that's a great question, something that we did not cover in the presentation. What considerations are unique to time series that aren't relevant to sequential data or to text data? One of the things is text data is always univariate. It's a sequence of tokens. It's discrete. Time series data is, in some sense, no, in every sense, continuous. Text data, time series data can be multivariate. Text data is, again, just a sequence of tokens. Other things that are really important for us to kind of take care of is the sampling frequency of the time series data, which also affects seasonality and some patterns. It's especially useful to know and model for forecasting tasks. We are not aware of analogs of that in text data. And also the second thing is amplitude. Different time series can have vastly different amplitudes. For example, heart rates are in microvolts. Meanwhile, economic data is in hundreds of thousands, if not millions. So those are some characteristics that directly come to mind that are really specific to time series data that modeling text data, that text data does not have. However, if I had to take a step back, there are similarities in modeling sequential text and sequential time series, and hence we are able to leverage a lot of advances in language modeling in building these foundation models, which is also exemplified by our use of transformers and the T5 architecture, which was initially developed for text data. I hope that answers your question, Emily. We also have another question from Thomas. What is their training task or tasks in pre-training? We are using mask time series reconstruction. So imagine how BERT was trained for language data. We're doing something extremely similar for time series data. We take a time series mask patches and have the model predict those patches and optimize mean squared error. It's not next token predictions, but it is filling masks with bidirectional context. We have another question from Lars. How does the performance compare with a gradient boosted model, I'm assuming, for GBM? We've not evaluated moment specifically with gradient boosted decision trees or any models of that sort. They're not state of the art for time series forecasting or but perhaps for classification. All the results are available in the paper, and I'm happy to answer more questions about them in detail. But we did evaluate moment on a lot of different models of different kind of architectures. Maybe some of them are gradient boosted decision trees. I don't remember exactly.
Then there's one more from Riyang, which maybe we can still get in today.
Sure. A question following the time scale issue. In real world case, there could be temporal heterogeneity. In that case, will foundation models agnostic to time scale overlook the implicit temporal patterns? I think that's an excellent question. And I believe that time series, in order to kind of build time series foundation model, we make certain assumptions. And the expectation is for these models to do well out of the box in zero shot settings. However, one other thing that we are actively working on and that we've always believed in while developing Moment is ease of use. So for example, if some data has these special properties such as temporal heterogeneity, it's very easy for us to kind of fine-tune models like Moment on such data or kind of steer model predictions in order to kind of take these into account. So I do believe that Moment might do modestly in such cases. I've not evaluated them specifically, but I do believe that with ease of use and access, smart researchers will definitely be able to make good use of these foundation models. But it's kind of hard for us to account for them when we're training a foundation model on so many different time series with differing time scales.
All right. Well, thank you very much, Artur and Mona again. Thank you very much for all of you guys for attending. So I believe both Artur and Mona are available if you have any follow-on questions. And as Artur said in the chat, you will find their email addresses on the first on their introductory on the first slide there. But and as we said, the slides and the recording will be shared hopefully by early next week. I think Riaz will be able to send email to everybody who registered to make you guys aware that the recording and the slides are available. So with that, thank you very much. And by the way, we have another great webinar coming up next week, next Wednesday, so 1 week from today. This one will be joined with NVIDIA and will introduce the NVIDIA AI enterprise framework and the components thereof that are also available on Bridges-2 right now. So hope to see many of you next week. Thank you very much.
Thank you all.